Should I get going?
Give me 1 second to start this recording.
Alrighty.
And go ahead.
Alrighty. Hello, everyone. My name is Will, as you all have known, and welcome to my senior exhibition. It means a lot that you all could be here and could come, whether it's in person, virtual, or even watching this recording after the presentation, since I know quite a few of you wanted to see that. And today, I'm going to be talking to you all about the perspectives behind harmonographs, which is the year-long senior project I've been doing as my Parker capstone project, so I'm really excited. So let's just delve right into it, shall we? Okay, great. So first, I'm going to talk to you all about my foundational learning. And basically, for this foundational learning, I needed to answer an essential question. And I decided to research the essential question, how could I analyze harmonograph art through different perspectives? And basically, in order to answer this essential question, I then needed to research all these different sub-questions. There are quite a few of them, as you can see, and I mostly looked into what the harmonograph is, some of its history, the math, the music, and I will delve more into the specifics of this question shortly in this presentation. Alrighty, so first up, you all might be wondering, okay, well what is the harmonograph? So basically, a harmonograph is a drawing machine, and it consists of 2 or more oscillating pendulums. There's one, as you can see over here, that consists of a stationary pen, and there's another that consists of paper that it draws on. And basically, this machine draws pictures based on curved lines. And what is so cool about it is there are weights that are often located at various positions to produce different patterns that oscillate, known as Lissajous figures. And basically, the curved lines that are created by the harmonograph resemble harmonic ratios, and these visually represent music. And what is so cool about these is they visually link sight and sound together. Also, just to clarify, a harmonograph is not a spirograph. They are different things. Harmonographs are pendulums which oscillate and are free to move around to create drawings. However, spirographs are bound within a circular space within a marker. And also shapes are drawn, but it's more controlled. So for this project, I was inspired by it last summer by working at the Discovery Museum, which is a children's museum in my hometown. And basically, while I was there, I heard that with their harmonograph, it visually linked mathematics, physics, music theory, and so much more abstract theory together, and I was just so fascinated by this. And when I asked them more about it, the museum actually didn't understand much about it within their drawings, and when I was trying to think of a senior project idea for the year, it gave me inspiration since it aspired to my interest in STEM. And nonetheless, here is to give you a rough idea of some of the drawings harmonographs make, some of which I made last summer from the museum. And here are some more drawings. So basically, these patterns represent many aspects in the natural world, such as, for example, hats, baskets, and if we go back to the last 2 drawings, from my perspective, this kind of represents a jellyfish and also a heart shape. So, yeah. And don't worry, you guys will see more of these drawings throughout the presentation. And, yeah. So most shapes that, you might be wondering about the shapes that harmonographs generate as they draw. So basically, most shapes that harmonographs generate are mostly circle and figure 8 variations that model Lissajous figures. And I will showcase some of these drawings later in my product, which is something you will all look forward to later on. And now, here are some examples of outlines of Lissajous curve shapes that are formed from harmonic vibrations. And also, these shapes, they vary between lateral and rotary pendulums, especially from harmonic ratios, which I sort of wanted to show you a sample in this diagram. And now that I've established the basis of shapes, I'm wondering about the different types of harmonographs. So, The shapes that I just showed you, they're created by lateral, rotary, and 4 pendulum harmonographs. And most often, the 2 harmonographs that are used are lateral and rotary. And both harmonograph types are the same length, and the table, as you can see, is stationary. And with lateral harmonographs, the motion of one pendulum moves the utensil back and forth, while the other is moving the paper. And with lateral harmonographs, as you can see, like the product I made, are pendulums that only move in one direction, which is backwards and forwards, and they create fishtail-like shapes. And meanwhile, rotary harmonographs, hence the name rotary, they rotate around in a circular motion, and they draw more rounded, circular, and shell-like shapes. Also, there are these really cool 4 pendulum harmonographs, which are extremely large, since the drawing surface is by 11 by 17 feet, which is humongous, as you can see in this picture. And there are 2 pendulums that each use the writing utensil on each side. And there are also compound pendulums within it, and basically these are held from 2 strings from a suspension, and from those 2 strings comes 1 string from the pendulum from the bottom, and it can swing backwards while also creating a circle at the same time. And also, there's the Blackburn pendulum, and it combines lateral and rotary pendulums, and it was named after Hugh Blackburn, since he was able to combine those 2 pendulums together into this one. And this pendulum is so cool, it involves paint where the weight is actually suspended from the air, and the paint actually drips off of it onto a canvas, and it creates all these different shapes, and I will showcase more of that later in the presentation. Alright. Now, I'm going to talk about its origins, and you might be wondering about its history. So, the harmonograph was invented by Hugh Blackburn, who was in 1844. And basically, Blackburn was a Scottish mathematician born July 2nd, 1823. And he was a mathematics professor at the University of Glasgow from 1849 to 1879. And Blackburn was a physicist and a mathematician, and his goals were to learn how to visualize how pendulums moved as a professor. And basically, he invented the harmonograph as a teaching tool, since he wanted to use the machine for STEM education, since its drawings end up linking the correlation between trigonometry, physics, and sound. And the harmonic ratios are represented through the pendulum's movement of the harmonograph. And ultimately, he took relationships that Pythagoras discovered with numbers and harmonies, and he made them visual through his drawings in the harmonograph. Also, initially, harmonographs were built for recreational purposes and in the 19th century, and they were toys that served little practical purpose. And then following the invention of the harmonograph, they became a new trend. They were found in many homes, and often stores back then sold portable models that could actually be folded into cases and taken to parties. And professional artists seemed to be the most interested in terms of buying them up, making them themselves, and actually owning them. It was like this really huge craze back then. However, unfortunately, after the early 1900s, harmonographs began to decrease over time in popularity and are rarely seen today except in museums. And now we're wondering, okay, well, what about these harmonic ratios you speak of? We want to learn more about that. So, I'm going to give you a history lesson. So basically, you all heard of Pythagoras. And basically, he is often described as the first pure mathematician within the Middle Ages. And essentially, he contributed to the development of a lot of the mathematics we see and use today, such as inventing the Pythagorean theorem. However, what is so interesting about him is we actually know relatively little about his mathematical achievements. And unlike many Greek mathematicians, there's actually no record of Pythagoras' writings. However, there is this one interesting story, where one time, Pythagoras was walking past a blacksmith shop, and he actually overheard ringing from hammers, and also realized that the weights of the hammers ended up affecting the sound frequency of the notes. And as he investigated further into this, it led him to discover what we know today as harmonic ratios. And he discovered, through his experiments, that a hammer weighing half as much as another sounded a note twice as high, which forms the ratio 2:1, since it forms an octave. And Pythagoras then went on to do further investigation, and found that all simple musical instruments work in the same way, that all nature consists of harmonies from numbers. And he then went on to identify that within natural harmonies, the same sequence of numbers appeared often, which were 16, 12, 9, 8, 6, and 4. And as he investigated further into these numbers, he found that they can be paired in many ways harmonically due to the harmonic frequency, which ends up being pleasant to the ear, and visually in these drawings, it ends up being pleasant to the eye. And as a result, Pythagoras' hammer experiments uncovered a set of relationships through octaves, and he found like other intervals within it, such as fifths and fourths, and those are the respective harmonic ratios I listed for that, but I will delve further into that later. And also, just to clarify, harmonic ratios are configured from the arrangement of harmonic intervals on a musical scale. They are not the notes themselves. You need to emphasize that. Because approximately over 2,500 years ago, Pythagoras discovered that harmonic ratios, which are simple wave frequencies, end up consisting of these simple numbers that I just showed you. And he discovered that these notes project frequencies that are 2, 3, 4, 5, and 6 times as fast as the tonic. And as he was doing this, he noticed that the strings that have simple ratios of their lengths end up creating many different variations of harmonic chords, since on instruments, strings can vibrate at low and high frequencies at different speeds. And as he looked more into this, he discovered that the sounds resulted in these simple ratios of harmonics that end up sounding harmonious together, which is why they are pleasant to the ear. And for example, he discovered that if one harmonic frequency oscillates twice as fast as another, they create the same note, which is pitched slightly higher, also known as an octave. And it ends up creating the ratio 2 to 1. And meanwhile, he found that there are simple frequency ratios within shorter intervals, such as 3 to 2, 4 to 3, 5 to 3, and 5 to 4, which as you can see form all these many harmonic intervals. And he found that these simple harmonic ratios form a basic scale that consists of patterns and also halftones. However, on the other hand, he looked into more complicated ratios, like 23 to 17, for example, and these end up sounding dissonant, which isn't so pleasant to the ear, and actually sounds a little icky sometimes. Okay, so now that we know what harmonic ratios are, I'm wondering, okay, what does this have to do with the art? What are the effects of that? So basically, these harmonic ratio relationships that I just showed you, that were discovered by Blackburn and Pythagoras, are modeled within the harmonograph drawings. And in a harmonograph, the frequency ends up measuring how fast a pendulum swings, for example, the number of swings per second. And he discovered that with the curves of the drawing, the length of the harmonic ratio will depend on the frequency. For example, if we take the length of the frequency and double it within the same note, again it forms an octave, which forms the harmonic ratio 2 to 1. And in this slide, here are some visual examples of harmonic ratios and the shapes that they end up creating through the harmonograph art. And I'll give you guys a moment to just take it in, just look at it. Alright. And basically, the harmonic ratio of bumps or lobes within each shape ends up matching the ratio of frequencies, as we know, number of swings per second. And you can see it clearly in this example. So in this example, as you see, there are 2 lobes in the vertical plane. And there are 2 lobes in the horizontal plane. And there are 3 in the vertical plane. Hence, if we take the ratio of the number of lobes in the vertical plane to the horizontal plane, they form the ratio 3 to 2, which is also known as a fifth harmonically. And I will elaborate more on how to identify these ratios with the harmonics as I get further into my experiential learning later on. So, now I'm wondering about the roles that Lissajous figures play. So, above, here are the closed Lissajous figure shapes, which often include harmonic ratios and many phases. And basically what a phase is it is the offset from the starting position of the pendulum, which is where this writing utensil is at the moment. And it forms angles and radians within the unit circle as it is rotating in a sinusoidal motion. And when you have two pendulums that are in phase, it is often referred to as a closed phase, and ends up producing simpler curved shapes like the circle. However, when phase or curved shapes differ more complexly, it is then called an open phase. And basically, the Lasigiu figures, they were some of the first fleeting pictures of harmony that were projected onto paper, which in a sense modeled the harmonograph art. And these figures determine the phase, frequency, amplitude, and so many other characteristics of a given waveform that are expressed within the harmonograph art. And the amplitude basically is how far a pendulum swings back and forth. And when the Lasigiu figures are formed, there are two sine waves that are applied simultaneously. And basically, they're often described by a set of parametric equations, which I will delve further into later. And for Lasigiu figures, I need to emphasize this again. If you end up counting the number of points at which the figure touches one of the horizontal sides and also the vertical sides, it perfectly resembles the harmonic ratios. And note that the figure will end up becoming more elliptic and will also become straight lines and even a circle when these ratios get further and further closer to 1. And now, I'm actually going to elaborate briefly on how the trigonometry measures these Lasigiu figures. And again, I will delve more into the specifics of the math and some examples of the Lasigiu figures later in my experiential learning. And basically, the trigonometry, since the motion of a pendulum consistently rotates in a circular motion, most of the time, as it is rotating, there are a set of perpendicular axes you all are probably familiar with, x and y. And it intersects directly at the center of that circle where the motion is moving. And basically, as it is moving, the number of oscillations is generally expressed in units per time, which is the frequency signified by the variable f. And t is also the time per oscillation as it is running. And as you can see on this graph example, the value of sine and cosine went from +1 to -1. And the value of sine and cosine is often multiplied by the amplitude at which the pendulum is moving, which is expressed as the variable a. And basically, sine and cosine functions are often referred to as sinusoids when this is graphed. So this is a sinusoidal function. And now you might be wondering about the harmonics. So basically, the Lasigiu figures can be formed from any harmonic instrument, such as the vibrating bells, motion of a piano, string within an organ pipe, and even the ring of a telephone. Basically any harmonics that you'll hear. And in the mid-19th century, Jules Lasigiu, who was a French mathematician, found that the vibrations between two tuning forks of the same length could be tuned to the same note. And he found through his experiments with those that if a small mirror was placed at the tip of a tuning fork and a light beam was aimed at it, then that vibration could actually be thrown and projected, as you can see in this photo, onto a dark screen. And when the tuning fork was struck, a small vertical line was cast, and then it was quickly cast sideways to another mirror, and it ended up producing a sound wave. And through his experiments, Lasigiu discovered that when two forks vibrate simultaneously, they would produce interesting figures that oddly resembled the same curvature within harmonograph drawings. And he basically concluded that the lines projected from the light ends up growing smaller and smaller and smaller until it eventually hit a point in the middle of that screen. And this parallels the movement within harmonograph drawings that I will also show you guys momentarily. And through these experiments, Lasigiu discovered that these figures depend on the harmonic interval between the notes produced by the tuning forks. And in other words, when a tuning fork is vibrating, a beam of light can actually project its vibrations onto a projection lantern. And the vibrations of the tuning fork end up passing through these lenses, and it ultimately forms this spot that moves back and forth into two perpendicular directions, kind of like the movement with these two pendulums. And the pattern repeats itself until the motion slowly dies away due to friction, inertia, and air pressure. And basically, these shapes that the vibrations make represent the shapes drawn within harmonograph art, since the harmonic intervals that end up being emitted from these vibrations blend to form harmonic ratios that you can actually identify within the harmonograph drawings. For instance, if only one tuning fork at a time is vibrating, it parallels how one note on the piano is vibrating, like middle C for example, and its harmonic ratio ends up being 1:1, or unison, since it is just that one note. And there can even be variations of other notes vibrating at a time that also forms 1:1, since it's just the one note at a time vibrating, and it actually creates many different versions of the circle in art, which is so cool. And now, I'm going to talk to you about the motion of the drawings. So basically, the writing utensil ends up moving side to side and also up and down sinusoidally. And most harmonographs have paper pendulums with the papers attached to them and writing utensils that drive over them to create the drawings. And as it is starting, a finite amount of energy is stored in the harmonograph as it, which is also a weighted pendulum, is pulled aside and then released. And within harmonographs, a writing utensil moves side to side in sinusoidal motion, and as it is doing that, the energy then gets lost in the form of heat, and it actually wears down as the utensil travels over the paper. And when a harmonograph is in action, the utensil ends up moving around the center multiple times until it arrives again at that center, or at that midpoint, where it comes to rest. And with harmonographs, as mentioned, there are compound pendulums, which are these weights at the bottom that are hung from fixed points, and this allows it to swing freely backward and forward. And basically, one pendulum carrying the paper is set so that it would not touch the paper, while the second, with the pen, is started. In this way, when both are swinging steadily, the pen is gently lowered down onto the paper. And when the writing utensil is pulled back, both pendulums end up being pulled to their highest point. And as it is moving, this is called the period of a pendulum, which basically is the time that it takes to complete one full swing, from one side of the pendulum all the way over to the other, and back again on the paper. And as the harmonograph swings higher, its period actually becomes longer. And also the period of the pendulum, just to clarify, does not depend on its amplitude. The amplitude is separate, it's the space within the drawing. And as it is moving, once it is pulled off from the start, the momentum carries it nearly from the same point from one side to the other. And as it is swinging, the pendulum loses energy due to friction at the fulcrum, and it ends up brushing against air. And eventually, the pendulum comes running down to rest at the center of its swing. And also, while the harmonograph is moving, a second pendulum can be let go, while the other is passing through the center of its swing, creating an elliptic shape. And the writing utensil is then lowered onto a paper, which produces a circle, kind of like this one. And it evolves into a single spiral. And basically, it continues downward, picking up speed until it reaches the midsection of its motion. And it then spirals its way outwards, and it sort of reaches this limit, returning before the pendulums run down. And at this point, it slows down, coming to rest, and I'll actually model this motion later with this harmonograph. And as you can sort of see in this drawing, the lines get toward the parameter, end up getting closer together as it reaches the center. Additionally, the frequency at which a pendulum swings is often determined by the distance from the weight to the pivot. And basically, the longer distance between the weight and the pivot often causes a greater frequency of the drawing, while the shorter distance between the weight and the pivot ends up causing a smaller frequency. And basically, the rotations or oscillations of the harmonograph are the relationship between the sound frequencies, or also the harmonic ratios and the pendulum frequencies. And that was a lot about its motion. I know, it's a lot to take in. But I've been wondering about the art, why it is so appealing, why does it stand out? So, typically, artists such as Anita Chowdhury, who ended up constructing her own harmonograph model, known as the Iron Genie, she believes that the aesthetic of the harmonograph is actually what is part of its appeal. And depending on the relative ratios, the harmonograph art of Lasciju figures represents natural phenomena that we all see every day. such as pretzels or nuts, and it can also commonly model seashell and flower designs. And you can even look at animals. So for example, in this diagram, right here, the LCG figure resembles a cat. And I'm going to delve more deeper into this other example. So let's take this drawing I showed you earlier. This beautiful green drawing. And as you can see, it kind of forms a heart-like shape. And what this is conveying is that within the natural world, hearts also include these LCG figure shapes and the proportions of harmonic ratios within them too. And ultimately, what it does, it creates the same pattern shown between the musical vibrations within harmony. And also, it shows us that within nature, there are so many abstract patterns within natural objects, such as hearts, for example, because they are symmetrical. And the symmetry is what is significant in nature because it shows that the formation within many different objects in the natural world, and it makes those patterns extraordinary. And yeah, that was my foundational learning. Now I'm going to delve into some cooler experiential learning I've done. And basically, here's an overview of the process of my experiential learning. And from the get-go, my goals have been to learn how to use different types of harmonographs, while then integrating my knowledge of mathematics and also this foundational learning I just showed you into the creation of the art. And basically, first I visited my mentor, John Fitzpatrick, in his harmonograph gallery in Newfane, Vermont over the holiday break. And this was a very insightful visit for me because I got to see the different harmonograph shapes and variations he's made in his gallery. And I also got to look at these two different harmonographs that he brought, a lateral and a rotary harmonograph, which helped me decide which one I wanted to build for this product. And I then wanted to start experimenting with my own harmonographs and possibly maybe visiting other ones at museums afterward. And the first is this paint harmonograph. And basically what this harmonograph is right here is it is a Blackburn pendulum. And I wanted to learn more about how it works, so I ended up interviewing Paul Wainwright, another harmonograph artist, since he used to have one in his barn that took photos of light drawings in the dark. And afterwards, I then continued to experiment with this paint harmonograph by actually setting it up in the classroom. And I then needed to learn about the parametric equations a little more, so I can understand the mathematics on a deeper level. Right before, I then began to experiment with the open and closed phases of the drawings by graphing them and making sure to link them to their harmonic ratios. And as a result, I bought this really cool toy lateral harmonograph to experiment with as sort of practice for using this product. And I began making a series of drawings, sort of fiddling around with the weights to create many open and closed phase variations of different harmonic ratios. And once I built my product, I know I keep pointing to it, but here you go again, the lateral harmonograph, I began experimenting with that as well. And first, I visited my mentor, John Fitzpatrick, at his harmonograph art exhibit at the Crowell Gallery in Newfane, Vermont over the holiday break. And my goal here was to get a general sense at how the harmonograph moved in person through experimentation, and to sort of see visually how they affected the art, and that helped me decide the details of which harmonograph I wanted to build as my product as I got to see those two harmonographs. And while I was there, observing some of his drawings and experimenting with those harmonographs, I got to learn more about the differences between their movements. And afterwards, I then decided to interview Paul Wainwright, who's another harmonograph artist who used to have his own Blackburn pendulum harmonograph in his barn. And I wanted to interview him in order to receive the necessary background on how to use a Blackburn pendulum so that I can use one in the classroom afterward for my experiential learning. And basically, just to clarify, a Blackburn pendulum is a bob suspended from a string, and this is one that I used. So basically, this bob is suspended from a string, and it hangs from this, it's supposed to make like a V shape of strings coming down from it. And basically, it's so that the pendulum oscillates back and forth, like this, into two perpendicular directions. directions with different periods. And the Blackburn pendulum, I'm going to show this again, and ends up using these wooden triangular pieces with a chain down of paint from the tube. And basically, this chain right here can actually be adjusted to up and down with the height from the string, like this, to create different shapes using the different lengths, and that ends up modeling different harmonic ratios. And with his Blackburn pendulum, on the other hand, what was so cool about it is he ended up using an LED in the dark, and he ended up taking pictures of it with his camera. And the Lasitu figures he made depended on how the harmonograph was adjusted at certain heights. And this way, he can actually control what shapes he wanted to make at any given time, and what his needs were as well, because he made a lot of art with that. Okay. And as I just pointed out, I first experimented with this paint harmonograph, which is a Blackburn pendulum, since I was curious about how it worked, and I wanted to learn more about its movement. And I basically decided to purchase this kit online, and then assembled it. Sorry, it's coming apart a little bit. Oh no, well, you can see it in this picture, I'll put this together later. Since I was curious about how it worked and wanted to learn more about it. And I then began filling the tube up with paint ink, and it was so much fun, because for these few days in senior sem, I made all these amazing drawings where I tried to link the harmonics and their respective parametric equations. And as you can see on the board over here that I just displayed, here are some of the paint drawings I made. And actually, I'm even going to pass these around if you guys want to see a close view, and make sure to pass them to the audience. Fortunately, I lost the actual drawings, but I was able to photograph them before they went missing, after they were painted. And yeah, so I did that, and that was so much fun. However, now you might ask about these parametric equations that I've been speaking of, and trigonometry. And this was the bulk of what my experiential learning was, because I then needed to do further investigation into them to understand properly how they will work, and now I'm actually going to show you. So basically with parametric equations, they're expressed in terms of time, and this is what's different from rectangular equations. And basically, for rectangular equations, which you're probably all used to by now, going through like middle school and high school curriculum, for rectangular equations, let's take an example with this function f of x equals, sorry, I meant to say x squared. Just look at this graph, it's generally f of x equals x squared. And in a general sense, in this function, no matter where I am on the graph, wherever I put my finger, the coordinates are always going to be expressed in terms of x, an x value of this axis, and an f of x value of this axis, or y, like they're interchangeable. And it basically only tracks two variables at a time, which we know as independent and dependent variables. And some real-world examples that may sound familiar are displacement versus time, or displacement vertically and horizontally. And yeah, you're probably all familiar with those. Those are rectangular equations. However, these differentiate from parametric equations. And basically what is different is parametric equations are expressed in terms of time. And what this means is that every x-coordinate and every y-coordinate that I just showed you in a rectangular equation will be expressed on its own in terms of time. And in some real-world examples, they basically track two variables, but again, each of those variables are in terms of time on their own. So here's some real-world examples. So for example, let's take the seconds elapsed per displacement of an object horizontally, and also the seconds elapsed of an object displacement vertically. And a way to think about this conceptually, because I know it may sound confusing when I say that they're expressed in terms of time, is just imagine watching a video of a ball being thrown. And as you're watching this video, you can pause the video at any given time to see where a ball is at any given point. And basically, that is what these parametric equations are telling us about where the position is at that moment in time when you pause the video, for example. And this was quite a process of learning. So first, I had to start learning the basic parametric equations. And I then began to go through more problems, and they ended up getting more challenging later, progressively through them. And for each, I had to start by solving for the rectangular equation using substitution. And then I eventually was able to graph both the rectangular equation and the parametric equation to see the overlap of them simultaneously. And eventually, I then started to, after doing a few of those problems, I then began using the trig functions. And I eventually was able to model the harmonograph drawings through the LCG figures, and I ended up seeing the harmonic relationships in these intervals and frequencies as I was drawing, or as I was learning to graph those equations. And basically, I started by only graphing the outlines of every LCG figure shape and ended up linking them with harmonic ratios. And I then discovered how to graph the actual drawings that the harmonographs make using something called variable called Euler's constant, known as E, and that makes it dilate toward the center as it keeps going. And when LCG figures are graphed by parametric equations, a clear pattern occurs within its outline. And basically, these are determined by various harmonic ratios, which are calculated by taking the interval of the frequency of two notes and then simplifying it further. And basically, the harmonic ratios are determined by the frequency, but also the wavelength of two notes, and then simplifying it. And the harmonic ratios are determined by the frequency and wavelength at two notes vibrating at different intervals. And these can be determined within any musical note of your choosing and scale. And it basically models the vibrations of the musical instrument, as long as the intervals anywhere any notes you choose are the same. And basically, the ratios occur within both open and closed phase LCG figures. And here's an example of each. So I'm going to start off by showing you guys a closed phase LCG figure. So basically, with closed phase LCG figures, they generally produce variations of pretzel-like shapes. And most of the time when graphed, they are modeled with parametric equations that have both x and y equal sine, and then the frequency of the note times pi in terms of time. And some even involve both cosine, but most of the time we just use sine. And with some, depending on the ratio, they can be modeled with parametric equations having both sine and cosine. Most of the time, they're just either both sine or they're both cosine. And these basically vary by amplitude and time, which are also multiplied to it. And I represented A as the amplitude and T as time. And basically, the harmonic ratios within them can actually be seen visually in these as well, by visually counting out the number of bumps and also intersections, as you can see like right here, between them. Along the x and the y axes, both horizontally and vertically. And here's an example that I used of a 6-to-5 closed phase LCG figure, which can also be an open phase that I'll show you guys in a sec. And basically, it models a minor third interval. And to give you a general sense, this is what a minor third sounds like. So that's an example, I will replay it, of a minor third, where I just played C and D flat, or sorry, C and E flat, or C and D sharp, however you want to interpret that. And basically, just to go back, this is the closed phase variation of that harmony that it's modeling. And basically, yeah, that was sort of the closed phase example. And now here's an open phase example on this next slide. And basically how to differentiate between the open phase and the closed phase is I'm going to go back. I know I just went to the side. But just imagine me, taking this point physically and pulling it out and pulling like all these points out. And as I am doing that, it is opening up the shape to look like this. And basically, I've taken a closed figure and I've opened it. So that is why. Hence it is called an open phase LCG figure. And basically, they produce variations of knot-like shapes. And the reason they are open, as I showed you, you just imagine taking one of those closed phase figures where it's tightened in into those intersections and then stretching them out further to create these bumps, which is why it's open. And most of the time, these are graphed by parametric equations that involve both sine and cosine. And with some, depending on the ratio, they can be graphed by both sine and both cosine, but most of the time, they're just graphed by sine and cosine. And these also vary by amplitude and time, which are multiplied to it. And the harmonic ratios within these are also seen visually. However, this time you only need to count the number of bumps within the points along the axes, x and y axes, horizontally and vertically. As you can see, as I've done in this diagram. And we heard what a minor third sounds like. And now I'm going to give you another example. We'll show this more clearly. So I'm going to show you, first I'm going to demonstrate how the harmonics overlap. So I'm going to test it using both the frequency and a wavelength of a simple octave. So for example, let's use middle C and also the C above it, which is known as C5. And basically, this is what they sound like. And according to this table, as you can see, I know there are a lot of numbers of these. Yeah, according to this table of equal tempered modern frequencies, generally the frequency of middle C, as you can see right here, is 261.63 hertz. Well, the frequency of C an octave higher, down here, is 523.25 hertz. And I know, these are big numbers, Will. Like, what are you talking about? These are decimals. But what's so magical about these frequencies is that if you take the ratio of these two frequencies from the higher C to the middle C, if you actually were to simplify it, what do you know? It forms that familiar ratio I've been telling you guys all about with the octave, 2 to 1. And what's so cool is you can do the same thing with a given wavelength, except this time you have to take the ratio of middle C and C the octave higher. And when I simplify this, what do you know? It's that same magic number. It's 2 to 1. Oh no, because my battery is running low. Okay, I'm just gonna, hold on. I'm gonna get my charger, sorry. I'm so sorry about this. Okay. Yeah, so as you can see, it reduces to a 2 to 1, which is an octave. And now, I'm so sorry about this, by the way. I need to keep the presentation going. Alright, so yeah, you see this familiar ratio 2 to 1 within the octave. So now, let's graph this. So, I'm going to graph this on Desmos. So, as I'm graphing this, I just need to check something. Alright. Yeah, so as I'm graphing this, let's use the open phase equation of sine and cosine and the closed phase equation of having both x and y equal sine. So, first I'm going to take away a, you guys don't know what that is yet. And what I'm going to do is I'm going to plug in this ratio we just identified, the 2 to 1 within the octave, into this sine and cosine function. So I'm going to make sine 2 pi of t and cosine 1 pi of t. And basically, I plugged it into it. And as you can see, it forms this amazing, sorry about this keyboard, it forms this amazing figure 8 shape. And for open phase, you can actually count the number of bumps or lobes along the horizontal and vertical sides. So as you can see, if I count 1, 2, there are 2 lobes vertically, and then there's this one at the top horizontally. And it forms the ratio 2 to 1, as I have just showed you, if you take the ratio of the frequencies, it's the same, it's an octave. And the same is true within the closed phase variation. However, one nifty thing I'm going to do first is I'm going to multiply the amplitude to it so we can see a harmonograph drawing being graphed. So the amplitude I'm just going to have equal Euler's constant, so that way I know it will dilate toward the center. And I'm going to multiply this variable by sine and cosine, and let's watch what will happen. And look at this. It now is spiraling its way toward the center, which is what the harmonograph is drawing. And I'm also going to show you the open phase variation. So if I plug in double sine, or closed figuration. So if I plug in double sine, it also forms that figure 8 shape too, which is really cool. And normally it wouldn't, it would form like a pretzel shape, but with the octave, it's a little unusual, it forms it. But the reason it's closed phase is if we go back to the open phase, you see how it's kind of open at this top, where it's starting? And now if I make it closed, it's perfectly closed, it's a closed shape. And with this one, it's different. You still count the number of bumps to determine the 2-to-1 ratio, but normally with other ones, you would count both the bumps and also the intersection to get the ratio within other closed phase figures. So nonetheless, I know that was a mouthful. Now, I'm finally going to get into this beautiful product that I've been telling you all about, getting ready for all this hype, which is the lateral harmonograph, right here. And basically, as mentioned, it consists of 2 oscillating pendulums, the drawing board, and also the pen and the marker holder. And basically, you can adjust and measure these weights to create different harmonic ratios. And what is so cool is that these ratios actually depend on the height up from these dowels. If you guys take a look on the floor, or like in this picture right here, from the height of each dowel from the ground level, kind of where my mouse is. And the only thing about this harmonograph is when I started experimenting with it, it actually mostly makes open phases more than closed phases. And for the building process, I actually had my mentor, again, Fitzpatrick, over Zoom for 4 days, as well as my neighbor, Bob Nephew, who actually helped me learn how to use woodworking tools, so that way I can execute all the necessary steps to put this together, since I didn't have much woodworking experience other than building like a tree house back, or not a tree house, a birdhouse back in Cub Scouts, which is a long time ago. Okay, so yeah, here's sort of the process of building. So the first day, I didn't want to waste time building a table since that wasn't really relevant or applicable in my project, so I ended up getting an IKEA table, which was very cheap, and I learned how to assemble it. And then the second day, I started meeting my mentor and my neighbor Bob, who helped me learn how to use a hand drill. And it was the first time I learned how to use a hand drill, which is so cool. And I ended up drilling these 3-inch holes in sort of this workspace for the table I set up in my garage. And I then screwed in the metal plates and made those marks on there. And then during the third day, I ended up drilling more holes into the metal plates. And I continued drilling on all these other bits around. And then I learned how to use a handsaw, which was important because I needed to cut these dowels to certain heights. So I was able to assemble some of the other parts that my mentor sent me because they were a bit complicated to carve onto the. And finally, on my last day of building, I finally finished the assembly. I got to screw in all the remaining parts, and I ended up attaching the pendulums onto the dowels. I finally got to add these cool weights on the bottom, and I then started experimenting and was able to adjust them to form harmonic ratios by measuring it from the ground up to where the weight is. And I conducted all these test runs for experimentation of it. It was so much fun. I got to make all these cool drawings. As you can see, I displayed to the right. And here are some variations I made of the open phase with the Lissiju figure 1-to-1. And as you can see, there are more on the board. But now let's adjust this to a minor 6. So since the harmonic ratio is 6-to-5, theoretically, I should be able to adjust one of these weights so that they are in proportion to each other, which luckily for me is where they are now, because I sort of adjusted them for presentation. However, before we make a drawing with it, I'm curious. This is sort of an audience question. So what do you think it will look like? As in, like, what shape do you think it will make? So I'm going to give you all a minute to think, and then I want you to raise your hand. And it's okay if you don't know. We're still going to see it. Alright. Yeah, what do you think it will make?
I think it'll be something like an oval.
Interesting.
Possibly. Who knows?
Yeah, who knows? We'll have to see. Alright. Do you have more guesses? Yara?
It's 1-to-1, right? I think it would be a circle maybe.
Yeah, that's if it's 1-to-1. This is actually gonna be 6 to 5. These were examples of 1-to-1. And
This
for
will
this,
be 6 to 5.
6 to 5.
Are your
It's gonna be an open phase 6 to 5. It's okay if you guys don't know.
And oh,
Open phase. Okay, what do you think? You have your hand over here.
Are these pictures on 6 to 5 or are they like different ratios?
No, those are different. Alright.
Okay.
What do you think?
I think it's gonna be like a square.
That is very interesting. Well, let's find out. I think you're onto something. So now, actually wait, before we find out. So sorry. Alright. Give me a moment. Alright, so who would actually like to come up here and try to make a drawing so we can actually see whether it makes that shape you predicted? Don't be shy, like, raise your hand. Alright. Well, Camilla, you've seen those people. Alright, yes, so you come on up here. So what I'm gonna do is you can come over here, it's fine. I'm basically gonna attach this piece of paper onto here, like so. And first what I'm gonna do is, okay, and choose whatever color you want. So, I can get it, I know these are hard to get. You want the green one. Alright, that's awesome. So now I'm gonna put this green marker down for you. And now one thing I want you to do is, can you push this pendulum so that it moves back and forth? Yeah, just push kind of hard on it, like kind of right there. Yeah. Yes, exactly like that. And can you push this pendulum so that it also moves back and forth? And great. You notice how it is kind of moving in sort of the sinusoidal motion? And I haven't taken the cap off yet, just so I can get a general sense at where the marker is going to move onto the paper before taking it off, because I don't want it to go haywire. So now, I'm not going to change its motion. I'm just going to quickly take this off while it is moving. I'm going to take the marker off, and I'm still keeping this moving back and forth. And now we're going to drop it. And look, notice how it is oscillating in sort of that sinusoidal motion I have been talking so much about. And basically it is wearing down its energy due to the friction. This is also due to heat as it is approaching its center. So basically all of those physics concepts I was talking about earlier is what is currently happening here. And notice how it is getting smaller and smaller as it reaches the center. And for those of you in the back, don't worry, I'm going to show you guys this in a second. So yeah, it is sort of oscillating as it reaches the center. So we're just going to give it a moment. And now, alright, I'm just going to wait for this to reach the very center. Great, it reached the very center. Alright. So I'm going to take this off. Camilla, do you want to hold this up for everyone? Alright, so look at this beautiful drawing. And as you can see, actually, hold on. I can hold it. I'll give it to you in a second. As you can see, it's a little hard to count, but as you can see, there are sort of approximately 6 bumps or lobes horizontally and 6 vertically. And that is because of the way these weights were adjusted. So here you go, Camilla, you can actually just take this is yours.
all right.
And now, we saw what that drawing is, so now let's graph it. So I'm going to go back to my graph, my nifty graph. And that was an open phase because, as you saw, it made that knot-like shape that you predicted, right? That looked like a square. So I'm going to make this open, so I'm going to make it sine and cosine. And I'm going to plug in that ratio 6 to 5. And even though it's not exact, look at this. Basically, we just made that drawing on the harmonograph, which is why it's graphed. And do you want to know something else that will blow your mind about this? Because it's the same. So if I write, I'm going to grab a marker. You guys might wonder what I'm doing, but there's a method. If I write the word harmonograph on the board, basically, what we graphed was a minor third harmonic. So hence, harmony, graphed, harmonograph. So we graphed a minor third, or minor sixth.
Oh, no.
It's okay. Mishaps happen.
Something.
It's all good. So yeah. And now let's tie this all together. So you might be wondering about my essential question, how could I analyze harmonograph art through perspectives? So basically, as we just have seen from a physicist perspective, harmonographs are significant because of the human interactions that we just had with the machine. And we can sort of learn how the science works by touching, feeling, and experimenting with it. And also, the universe is full of oscillators. There's the pendulum, pipes of air like within a flute, the mass of a spring, and so much more. And in a nutshell, the mathematics that govern all these oscillators is the same because it is directly applied in the harmonograph art and also harmonies. And the Lasicu figures are significant, furthermore, because engineers, during their jobs, actually use the principles of them to tune and set up signals that they send out through sound waves. And with the music theory, it is sufficient because it shows that connection between the harmony of the sound, the Lasicu figures, and their symmetry within the natural world. And that's sort of why it's significant through an artist's perspective, because you see all these many abstract patterns every day in nature that include that symmetry principle. And now here are sort of my works cited, but I'm going to skip through this very quickly, that I used for my research. And thank you all so much for watching. Do you have any questions?
Okay, so we're gonna go to the questions in just a second, but first I just wanna say that that was quite impressive time-wise. You were at 57 minutes. Okay, nicely done. Okay, so this is the phase where the jury gets to ask questions. I usually like to start on one of the ends. Would either of you like to begin?
I have so many questions. Okay. I'm going to ask about your process in designing the product here. So, like, I know you did a lot of research, you looked at a lot of different kinds of models, but then you decided you wanted to make your own. And you got the IKEA table, which I think is very fun. But then how did you really know, like, how to design it? Like, what was your process around making the plans and knowing what kinds of parts you needed to buy? And where did you buy the parts?
Actually, a lot of that is thanks to my mentor sitting next to you, Don. This is actually an idea from one of his lateral harmonographs he made in the past, except he didn't use an IKEA table. He was actually able to make a wooden table from scratch, and he generally helped out with, like, since again, I'm not an expert on the woodworking, like he helped me plan the design on like the measurements, on where to measure and cut things, and sort of gave me explicit instructions on those through the Zoom meetings we had, and also a list of parts to buy for that, such as the certain screws, the certain weights, and basically after doing that, I then went through the process of building that I just talked to you guys through for the product.
Awesome. Can I ask one more related question?
Sure, you guys can ask as many questions as you like.
That's
Awesome.
not actually true. We can ask one question each.
Can I ask my follow-up
Yes,
question?
you can ask a follow-up question.
All right. So you talked about sort of the drawing that you planned Camilla to make, right? Like, how did you know how to adjust the weights specifically to plan for that 6:5 ratio you wanted?
That's a great question. So notice this nifty ruler I have right here. And as you know, basically, it's not actually the weights themselves. The weights are the same on each side. It depends on the length of where the weights are from the tip, from the bottom of where this is at, to where they're adjusted now. And even though it was a little hard for me to fiddle around, I'm not going to tell you the exact measurements. It's a little hard to read on this ruler. What I did a couple of months before was I basically tried to measure. At first I was trying to make an octave, but that was a little harder to do, so I ended up just putting it at a certain position and ended up measuring the weights in terms of like inches or centimeters, either one, and like when you simplify those measurements in proportion to each other using math, it ended up forming that harmonic ratio, which is how it was drawn on here. So I know it's a bit hard to conceptualize a little bit, but that's kind of how it turned out, which is why it's so magical. It's like a magic number that occurs within the harmonies, how the weights are adjusted, and in the drawings.
Thanks,
I have a question about, really enjoy learning about the math of the harmonograph, because as an artist who's been building them for a while, I'm really only interested in the art and the patterns that they make, so understanding the mathematics is really interesting to me. I'm wondering if you ran into any similarities between the ratios that you see in the harmonographs and the golden mean or the Fibonacci ratio?
Oh, that's also a great question. I only learned a little bit about the Fibonacci sequence a couple of years ago, but I think in terms of the numbers I was sort of talking through earlier when I talked about how Pythagoras discovered those harmonics from that set of numbers, and then discovered the frequencies and the weights and the speeds. Basically, sort of that set of numbers that he was looking at, I think, are probably the same or relatively close to the sequence of numbers that occur within that Fibonacci sequence that is reflected through golden ratios. I know this sounds very complicated, but if you were to look at it visually, it's easier to see and to conceptualize than me describing it. So
Thank you.
All right, I want to throw this softball because I have been asking you variants of this question all year, and I really enjoy every version of your answer to this question, which is, this is such a niche project. Just senior projects are always kind of niche, but this one in particular is so specific, and you love it so much, and I want to know why. Why do you love this so much?
I love it so much because it's kind of magical the way you look at it in retrospect, because there are all these things we learn about in class, or even things you see every day, like objects and math and all these physics, and you learn about all these things on their own and sort of separately. But what is so fascinating about this one project is it combines all these different things together to tell one story about how this art is made, and sort of other contexts in real life where you can sort of see it, and also you can see where these numbers come from and why they're significant and sufficient to show harmonies, sound, and nature all visually, versus sort of just seeing it and being like, oh yeah, there's a piece of nature, or there's a piece of beautiful art. It links all this together in one, which is what is just so fascinating about this, and why I just love this project, because it was so fascinating to learn about it, and that's actually what gave me that inspiration. The museum themselves actually knew that there were these concepts that linked together, but they didn't know how. And that was this is perfect for me to investigate, because I'm just so interested in this.
Okay, so on the next, will you continue to make harmonograph art in the future? Will it become a hobby or something?
Maybe not a hobby, but probably I will in the future, in my spare time. And I'm actually hoping, I'm still thinking about this and might give this to Parker, but I'm working again at the Discovery Museum this summer, where they have their harmonograph, and definitely there I'm helping other people learn how to make harmonograph art while I sort of talk about my project, because they were even fascinated there about when I told them about my project. And I might even showcase this in museums. So I think that's sort of my future with harmonographs, but I don't think it would be a huge hobby, especially because I'm going to college soon, but definitely something I continue doing and have fun with, certainly.
Okay, well, this is the point where the jury gets to say nice things. So we could go the other way or go the same way. Do you want to start?
Sure.
All right.
Your project is really interesting how art and math are so intertwined with spirals and everything like that. I'm not so much of a math person, and the way that you were just so entertained and I'm trying to find the word, but I can't find it. You just really enjoyed, it just seemed like you really enjoyed the math portion of it and the result that you got from it.
I find in talking about the work of my advisees that I realize that I'm supposed to talk about the presentation, but I really mostly want to talk about the process of how you got here. And Will, in particular, got here through just an absolute willingness to keep working hard at every single interval of this, right? If he got the feedback that he wasn't clear enough describing how the math worked, or he didn't know some particular concept clearly enough, he just was a machine. And he would figure out how to explain it, or how to do the thing, or how to build whatever it was he needed to build. And it was just so impressive how determined you have been all year, and how much joy you took in your accomplishments. It's just been inspiring to watch.
And I would just like to say, as someone who uses the harmonograph as a tool to make art, understanding the math you really simplified it for me, especially when you show me how to count the lobes and the intersections to find the ratios. And I think that's really going to help me in my art in the future to come up with new patterns.
Will, I wrote down some words that you said or sort of came to mind when you were describing why you love this so much. And I added some of my own ideas, which I think is really fun to have, known you for 6 years. But this product and presentation, and I've seen little glimpses of it throughout the year because you've shown me in class, involves so much about you that you really love and embody, which is like music, math, art, nature. You are so curious, you are so precise. You've got a really strong habit of inquiry, and you dig really deeply in your investigations. And all of that had to be true about you, I think, to land yourself here. And this was just such an intriguing presentation. I found myself feeling like I was in a math class, and I wanted to really try it myself and change it just a little bit to see what happened. And I know that that's kind of the same way that you approached this, and it was really, really my honor to be able to watch you do this today. It's awesome.
All right, well, that's an excellent note. This is the time to cease the recording.